Hi there, it's Paul with a colorful graphical illustration of what it means to integrate a vector field over a parametrized curve. In physics, this is referred to as a line integral or sometimes as a path integral. I couldn't resist being able to do this with fancy colors and finally discovered the color ramps library. You'll need to install this package in order to use it. I, of course, commented out the install.packages line because I've already done the installation, and we're going to be taking derivatives again. So let's set up a parameterized path and a vector field. For a parameterized path, we need a parameter interval that runs from A to B and a parameterization function that maps that interval into a curve in the plane. This curve may or may not be a manifold. It doesn't make any difference. We also need a vector field. So for my parameterization function, I'm going to use a first component, which is the tangent of the parameter t, the second component, which is the secant of parameter t, because secant squared minus tangent squared equals 1. This will plot up as a nice looking hyperbola. And so there's my parameterization function, a vector valued function of t. And since the parameter is an angle, I'm going to run it from minus pi over 6 to plus pi over 4. Here's my vector field. I have two functions of x and y. I want to plot both the parameter space and the curve on the same diagram, so I've specified a y value where the parameters don't get in the way. Let's set up the plot. We're going to break the parameter space up into 40 segments, and therefore we need 41 values ranging from A to B. And for each of these values, we're going to have a color, and it turns out that magenta to green gives us 41 nice colors that range from magenta at the low end to green on the high end. I don't want my vector field arrows to be too long, so I'll multiply them by 0.1. Our sum is going to hold the sum that approximates our integral, and now we are in business. I will set t0 and t1 to be two consecutive values in parameter space, 1/40th of the distance from A to B apart, and I will draw an arrow with the ith color in the color sequence to show that. Then I will move on to the curve. Function g1 gives me the x component. Function g2 gives me the y component. I need to evaluate that for my two consecutive parameter values, t0 and t1. And now I'll be able to draw a nice looking arrow. Finally, I have to plot the vector field, which has two components given by the functions f1 and f2 evaluated at x0 and y0. Once I've computed that, I'll start approximating my line integral, and what I'm going to do is add on the dot product of the vector field at a point on the curve times the increment vector at the same point on the curve. That's pretty abstract until you plot it up, and now you can see what's going on. On the bottom is our parameter space. We've just broken up an interval from A to B into 40 equal pieces. Each of those 40 pieces gets mapped into a correspondingly colored vector on the hyperbola, and at the left endpoint of each of those vectors on the hyperbola, I've plotted the value of the vector field. If you're doing physics and trying to calculate work, you say along each portion of the curve, the work that's done is equal to the dot product of the force, that's the black arrow given by the vector field, and the displacement, the colored arrow that runs along the curve. And to approximate the work done, we want to add up all those dot products, and we've done that, stored the value in the variable rsum, So there's an approximate value of the line integral. Now, in fact, nobody ever does the calculation that way, because it turns out to be perfectly easy to do the same calculation without ever leaving parameter space. So this time I'll store the answer in RP sum, make note of the increment between parameter values, and do the same sort of calculation. Now I have to calculate the vector field, and starting with my value t0 in parameter space, I apply the functions g1 and g2 to get the point on the curve, and then I evaluate the functions f1 and f2 to get the vector field at the parameterized point. To get the little vector that runs along the curve, all I have to do is take the derivative of the parameterization function and multiply it by the appropriate increment vector, which is a constant. And then I just sum up the dot product of the vector field at a point on the curve with the vector that runs approximately from one point on the curve to the next. Previously, I was using a vector that ran exactly from one point to the next. Now I'm using only the best affine approximation to that, so I don't expect to get exactly the same answer. And I don't. Instead of 0.39, I get something closer to 0.37. Now we can do much better if we simply use the midpoint of each interval in parameter space and repeat the calculation. The only change here is that to t0 I have added half the increment, so I'm evaluating both the little vector along the curve and the vector field at the middle of the interval. And with that change I get yet a different number, 0.42. To turn this into an integral, I have to pass to the limit. What I've really calculated is a Riemann sum. But it's easy to figure out what we want to integrate. What I have to do is the equivalent of computing the integral of power over time, if you're thinking of physical terms. So starting with a time t, I apply g1 and g2. That gives me a point on the curve. I evaluate f1 and f2 at that point to get the value of the vector field corresponding to the time t. Remember that gradient in R also just takes derivatives, so I take the derivative of the two components of the parameterization function, g1 and g2, calculate the dot product of the two, integrate that from a to b, and I get remarkably close agreement. What's going to surprise you is that this last calculation is actually the definition of the line integral. Line integrals are evaluated in parameter space. They're just plain ordinary integrals, and all I did with the curve and the fancy colors was providing a physical motivation for that definition. Now let's see what happens if the vector field that we choose to integrate is a gradient. I've written down some messy looking function of x and y. Doesn't make much difference what I use. Evaluate its two derivatives and tell R the formulas for them. And now do exactly the same calculation. I'm not going to read you the details because you've seen this once before. Different vector field, same curve. Different value for the line integral. I can do better, as before, by using the midpoint. I can actually set up my function in parameter space and get the answer as an integral. But in this case, there's an easier way to get the answer. Since the vector field in question is the gradient, all I have to do is evaluate the function whose gradient I took at the right endpoint of the curve. That's the point whose coordinates are g1 of b and g2 of b, because b is the right endpoint of the parameterization. Do the same thing for the left endpoint of the parameterization interval. Take the difference between the two, and presto, I get, apart from some slight numerical discrepancies, exactly the same result as doing the integral. A nice way to visualize this is to add the contour lines of the function little f, whose gradient was our vector field, to the plot. And when you do that, you can look at the curve and see that at every point on the curve, the black arrows, which represent the vector field, are perpendicular to those contour lines. Effectively, what we're doing as we're moving along the curve is just moving to higher and higher contours, and the effect of the integral is to take us from the contour line at the left end to the contour line at the right end.